Yes, hello. Am I audible? Yeah. Hello. Wait, am I audible? Yeah.
Yes.
So, yeah, so as you know, it's just going to be an NTPSS. Feel free to stop me whenever you don't understand anything, and whenever like a problem is being discussed, just ask me. Like any ideas, feel free to share any ideas around it. Oh, wait, I did not take this. Hmm, interesting. Yes, people. So these are the problems we have. You are free to choose the problem you decide. Like, which problem do you want to start with first?
Where are the problems? It's not visible.
What?
Where are the problems? It's not visible.
Oh, the problems are not visible. That's better. Okay. Yeah. So let's just start with this one. It's better if the problems are not visible. Yeah. Yeah. So this is like, we'll start with somewhat of a scam question and then proceed. So, like, try the problem, and if you don't understand anything, ask me. Also, if you people have done any like a problem or want a harder problem, ask me. I'll tell you. Yes. Any thoughts on this? Like anything you people have tried or whatever?
Could be a counterexample.
Yeah, like exactly. That's the point. Like, see, it's probably a counter exam. Like, can you give me like a reason you think?
Wait. I guess I've seen this problem now. When you mentioned it's a counterexample.
What?
I guess I've seen this problem once. Now you mentioned it's a counterexample. Is N25.
Ah, so you've seen the problem. Okay. Wait. I'll give you another problem. Yes, so like, but for those people who have not seen this before, try to think which of these is more likely. Like, will there be an example or will there be a counter example? Uh, yeah, those who have done the problem, try this problem, and if you have done this one as well, DM me. I'll give you an extra problem.
I think that if we have n even, then this will always be true.
And then this will always be true. And why is that like a guess or something you came up with?
I think it's a true because then if n is even, we can take 4 to the n by 2 is a power of 4, which is 1. So then eventually it will just loop back to 1 and always it will be
Hmm,
a power of 4.
true. I'm sorry, there's like the dog is barking. I'll throw him out and come. Yeah, sorry for that. Yes, so yeah, Bhairav, as you were saying, so it's true for N, but what like anyone thought of that? Why like which do you think is more likely to happen? Will it be true or not?
I think it will not be true, but maybe it could be true also. It's also true for all prime numbers. No, all
Right.
prime number 2 to the n minus 1 is a prime.
Yes.
Yes, I think we should start looking for 9.
Hmm. Nice. Yes. So see, instead of like anyone else, like anything you people have tried, it's fine even if you have just like tried some cases or anything. Just tell me what have you.
So we kind of have to prove that the remainder left by 2 to the power n is one of the n remainders in truth bar. I mean, one of the n remainders in truth bar n minus 1, which are powers of 2. Powers of 4, sorry. So n by 2.
Yes, but wait, why are there n powers of 2 and less than 2 to the n minus 1?
I mean, because we have to take a remainder. So, I mean, not,
Yes.
we need powers of 4 actually. So actually make it n by 2, I think. Not n by 2, n minus 1 by 2 actually. Because, no, wait, you can count 1 as a power of 4?
Yeah, you probably can count one of them. So
Then,
what you're trying to do is we have to show that like 2 to the n belongs to this set which is all the powers of 4 modulo 2 to the n minus 1, right?
yeah.
Right. So like can you comment something about the size of the set, how large this is?
One thing, uh,
Yes.
you mean all the powers of 4 which are less than 2 to the n minus 1, or all of them modulo 2 to the n minus 1?
Modulo, not less. Modulo.
Then, well, 2 to the n is a power of 4, so
Oh no, wait, sorry. In this question, as they're asking us about the remainder and not modulo, will like strictly care about the less part.
okay.
Yes. So like any remainder say that's like 4 to the k has to be strictly less than 2 to the n minus 1. Yes, Ronit, do you have to say something?
Yeah, for 2 to the power n minus 1, if we
Hmm.
multiply that by 2 to the power 2 to the power 2 to the power n minus n, okay, the 2 to the power,
Wait,
yes, the whole thing to the
multiply
power
this
of 2.
this.
No, no, all of 2 to the power of
This.
Can I write in the, okay, fine. Can
Wait,
I annotate?
wait, are you people allowed to annotate? That would be easier.
Yes,
Yeah,
that
just
I'm,
yes. If you are
can you
able
see?
to annotate this one. Yeah.
All right. So 2 to the power of this thing,
Yes.
or n minus 1.
Yeah.
This would be like if we took this, then we'd get a multiple over here of 2 to the power n minus. So I was trying to see if I could use this
Hmm.
to find possible multiples. So like trying to get closer to what the end remainder could be if it's power of 4.
Yeah. Exactly. That's a great idea. So see, so how we will use this is, wait, I'll erase this. Yeah. Yes, people. So see this. Observe that 2 raised to the power n is actually congruent to 1 modulo 2 raised to the power n minus 1. Okay, it's very obvious thing, but this is what will help us to solve the problem. So we see that 2 raised to the power 2 raised to the power n will be congruent to 2 raised to the power 2 raised to the power n minus n modulo 2 raised to the power n minus 1. Does that make sense to everyone? Yes or no? Okay, good.
Yeah.
Yeah. So see, we keep repeating this, and eventually, like this again, we will get is congruent to 2 raised to the power 2 raised to the power n minus 2n, and we keep doing this thing until we hit 2 raised to the power 2 raised to the power n, but the power is modulo n, right? Yes, where?
It turns out actually 25 is the smallest counterexample.
Yes, indeed, 25 is the smallest counterexample. Why is it the smallest? I'm not sure about the smallest. Wait, why?
Because if you look at all even numbers, then it will have to be true. All prime numbers actually, if you do the same way, it will become 4.
Yeah.
And then you just look at the remaining numbers, which are 9, 15, 21, 25. Below
Those
20.
don't work. Makes sense, makes sense. So like you essentially just case bashed it. Yeah.
Well,
So
there
see
are
for
only 4 cases, so
yeah. So like I'll just go over the solution. Till then I'll give you the next problem. Wait, do you people want to try an ISL or something else? Like we have an ISL and we also have a USCMO problem. Which do you want to try?
Which USCMO?
Oh, let's try USJMO instead. That's better.
Yeah.
Oh wait, no, this is a very scam problem. Sorry. Like ideally we should not have two scam questions in a single class. Yes, people. So this is the next problem. Just like take a screenshot or something. I'll complete the other solution.
Oh wait, we did it in the last time. We could not take the session.
Ah, interesting. Wait, did you do the factorial thing?
Which factorial?
I'll show you the next problem then. Yes. Have you people done this one?
Yeah, it's ISL. Okay, got it. No.
Wait, have you people solved it or do you know this one?
No. Like we have not done it, but I've seen
Yes.
it.
Okay, so you try the buffer problem then. Yes. So everyone took a screenshot and stuff, right? I'll go to the other. See, so this problem. So firstly, what motivates us to show that there is a counter example is this thing, right? We do this, and this then essentially claims that 2 raised to the power n modulo n is always even. Like that just sounds wrong. And this is essentially the motivation that 2 raised to the power n being even for all n just sounds wrong. So obviously we see that if I let n equal uh, if I let n equal a even number, then this will obviously be even. And the rest is just case bash. The actual solution just says that last step is just check all values of n till you find them. Exactly. Like going off on a tangent, I think like this problem, Zooming said that it was included because the previous year the USA IMO team missed problem 5 on the IMO, which was like similar guess. Anyways, no chit chats right now. Yeah, so this is the problem. Try it and tell me or any progress, or like if you don't understand the problem and explain it. Stuff.
I think for odd n that are not equal to 1, it can't work.
What?
If we take an odd n not equal to 1, it
Yes.
can't.
Like the last time I tried, I proved that no even works.
Yes. Bhairav,
And
I think you also mean even. Like, could you go on?
Oh, I must have gotten confused.
Yes,
But
probably. Yeah,
I
say.
suppose you can just take n factorial minus 1, yeah.
For odd.
Yes, sorry.
Yes. So this is like one solution, and this does not commute to another.
Yes, yes, if n is even and not 2, then it won't work.
True. And why is that?
Because then you also get a to the power of some even number is minus 1 mod 3. So that doesn't work.
Yes. Right. That is correct. I'll show you another thing. So what Bhairav essentially says that if 2 divides n doesn't work. So like the proof is pretty simple. Assume that a works. Right. Assume that a raised to the power n plus 1 is congruent to -1 mod n factorial. Then what you can do is replace a with negative a. It becomes negative a to the n plus 1, and as n is even, it just becomes a to the n. Sorry, wait, this is 0. Yeah, this just becomes 0 again. So whenever a is even, you get two solutions. Any problems with that? Like that even and that do not.
We could also look at like a to the n is -1 mod n factorial, and like
A
if
to the n.
n is greater than 2, then like if we check mod 4, then it would be -1, which is not possible.
Yeah, exactly. Like a similar argument was provided by Bhairav. He did mod 3. Let's
Okay.
wait. There are out of space. Okay, I won't have space.
Actually, if it's a multiple of 3 which is greater than or equal to 9, we can take 7. And then there are either 2 solutions. There are at least in 7 there are 3 solutions to that, right?
Uh,
That
wait, what?
if we take it, if it, if n is a multiple of 3 which is greater than 6, we can take 7. And then we get,
Multiple of 3 greater than 6.
yes.
Okay, so
So
n is equal to multiple of 3. Yes.
then 7 will be there. And then we can take it mod 7 and we get 3 different solutions. If there is one.
Ah, yes. Exactly. Great, that's clear. So, yeah, that is indeed true. But like, if you're given such a problem where they ask you to find the n, so it's a good idea to try small cases, but a lot of the times what happens is that you do not have like, what if the smallest case turns out to be like some weird thing like 2 raised to the power 256 minus 1, something like that. So try to bound the values of a and b which you can achieve. Like you have a prime there, and primes are like pretty good. So using that, try to bound the values of a and b.
So can we state that A cannot have a prime in the range 1 to n?
Uh, Wait a minute. Yes, a cannot have a prime in the range 1 to n. Wait, why is that?
Because that prime will exist in n factorial, and if it does have a prime in A, if A does have a prime, then that prime divides 1 mod prime. So,
Yeah, yes.
but it's a small bound, so I don't think it's anything useful.
Mm.
But that reasoning can also be the reason why n can't be even, because n does not have the multiple factor of 2. Because like does not work.
Yeah, that's true. That also shows why any event does, because anything you take will obviously.
Can we think in terms of orders here? Like,
Yes,
because
yes, because that's good. So
because what I
mm,
found is that a to the n plus 1 is congruent to 0 mod n factorial. So you will just get that 2n is the order, because a to the 2n will be 1 mod n factorial.
yeah, like a to n is indeed the order. Mm. Wait, what if n is odd and 2 is the order? That could also be a case, right?
No, like a to the n is not n is not the order, right? Achha,
Yeah,
right, it
but
is. Yeah, works. That kind of stuff. Okay.
yes, yes, Bhairav. And Bhairav, you can just like start to speak it. You don't have to raise hand. Just wait for the person to finish and start.
Is there any theorem that for any prime or any number n,
Hmm.
there's a prime which is congruent to 1 mod n, which is less than n square?
Wait, what? I could not get you.
Is there any theorem stating that if we have any arbitrary number n, there'll be
Yes.
prime congruent to 1 mod n, which is less than n squared?
Uh, no, I'm not sure. I'm not sure about that.
Okay, thank you.
Yes, you could probably try bashing it by like both, like some that like there exists a prime between n and 2n. So maybe try bashing it with that, but not sure. Is that necessarily true?
So we just know that order of A divides 2n
Yes, that's true.
for any prime in the range.
Yes,
Well,
1 to n.
order of a can only be 2 or 2n, right? Because n is odd.
yes.
So if you
Wait,
consider odd,
again, what if, wait, again, what if A is just, oh, sorry, yeah, it can only be this. So let like P be a prime that
Wait, but
divides.
what if the order is something like 2k where k divides n?
What?
I mean, the order instead of being 2n or 2, it is something like 2k where k divides n.
All right, that can
Like
also be
wait.
the case.
Yes. So see, we get that this thing holds.
Yep.
Yes. So we essentially get this, but what will you do after this? As Harshit said, you like can't really get a good value out of this. Right?
Also, one thing which I have an idea, like a very random, that
Yes.
a to the n plus one is given LTE vibes.
True. True. A to the n plus one does it give LT vibes. But see, LT is true. We would probably use LT, but see, when you have like want to just raise it out, you would take a prime that divides a plus one, right? And wait, let me think. Yeah, LT will actually be very good. Wait, yes, so let's see. People, so what we have is this problem.
Sorry, could you repeat what you told for the LTE point?
LT would be good. LT, yes, we will use it. So see, we have this thing, and as it stands, we have this thing that order of P modulo A divides this. So when you see this, what do you think should like? How could you make your life easier here? Okay. So when I saw this, I was like, if n were to be a prime, some prime q, then observe that the order can only take finitely many values, right? So explore the case where n is a prime, because then you have to worry about less values. Wait, did that make sense? Like, why should we look at primes?
Yeah, got it.
Yeah, and in general, it's like a rule of thumb whenever you have to like find stuff, try special cases like prime.
Wait a second. So if you take q to be a prime, and
Yes.
if you get that q factorial divides a to the q plus 1, is if you take n to be a prime q, so you
Yes.
get q factorial divides a to the q plus 1. Now, which implies that q divides a to the q plus 1. That means that a to the q is congruent to minus 1 mod q, but we know that a to the q is congruent to a mod q because it's by
Yes.
FLT. So you
So we
get
get that A is congruent to negative 1 mod. Right. Wait, everyone followed that, right? Any like problems?
Wait, can we use induction now?
How are you planning on using induction?
Because if we know the statement for q minus 1, then we use the Chinese remainder theorem since q is prime. And we get
Yes, that's a good idea. But like that's an idea. But see, here we were able to write that A is negative 1 because the exponent had Q. So if it's some other prime less than Q, then we can't do this because it will not divide Q, right?
Yes, but if we just know it for that case, we can just use the Chinese remainder theorem.
Wait, sorry, I don't get what you're saying.
So if we knew this was true for q minus 1, oh wait, but if it might not be true for q minus 1, right? Oh yes.
Yes, exactly.
So we just know that if a solution exists, it's of the form -1 mod q.
Yes, it's on the form minus one property. Can you people like find a solution? It's like very apparent. We also find it above. We found it like
It's
just
it's
moments
n
ago.
equals 1, right?
What?
N equals 1 is a solution.
N equals 1 will obviously have a solution, and that will
Okay, what solution are you asking us to find?
what?
What solution are you asking us to find?
No, I'm saying when you have that p is a like n is a prime. Can you find a solution when n is a prime?
Okay, got it.
Right. And like obviously you can take n to be like the prime to be greater than 2 because 2 can be done with hand.
Okay, so just take n equals 3 to check that 9 divides a cube plus 1. Okay, 2 cube. So a equals 2 works. A equals 2 and n equals 3.
Yes. Like can you generalize that? Like for a general prime p, what do you think will be the
P
solution?
minus 1
Uh wait, what?
P factorial minus 1, sorry. P factorial.
Yes, exactly. So like if we have like that n is equal to a prime p, we see that p factorial clearly divides p factorial minus 1 to the p minus 1.
I think it's
Right. Yes.
+1 in the.
Oh, yes, sorry. Plus 1.
Yep.
Yes. Like try to work out the values of smaller primes by hand because it's not that hard. Like try 579, 357. You can try 11 if you like have the guts of computation. Don't.
Okay, so we got for n prime.
Yes, we have found one solution. We have not proven that it's the only solution because we want it to be exactly one, right?
Actually, if we look at it for 4, it's not true.
N equals 4.
Yes.
Yeah, remember we had shown that n equals like any even number just doesn't work.
Wait, I didn't get that step where n is an even numbers, but you took like -a and a both will be solutions, right?
Yes, because see, essentially if n is a number, we can write n is an even number. We can write n as 2 to the k, 2k, right?
But isn't it written like a greater than equal to 0 in the question? I'm not sure.
Oh, sorry. Like, see, here I had a congruent sign. I meant that negative a is negative in the
Oh,
mod
mod.
sense.
Yeah, mod. Okay, got it. That's what I was missing, I guess.
Yes. Wait, I'll drag down the question. Yes, people, like, did you find anything? Have you found anything?
Also, I just had a random thing popping that if you take no, like you leave this for time being. Now, if you take n equals any p times q, where p and q are primes,
Yes.
so you get that a to the pq is converted to minus one not q. So you get that a to the p is converted to minus one. So
Yes.
so like you get q divides a to the p plus one. You get a similar form. So how and it helps.
Hmm. Yeah, that will, but that won't always be necessary, right? If you take PQ, that's fine, but you have a factorial on this side, right? This will have like a lot of primes. So I don't really see how that will help.
Like for PQ, if you think that the only two primes will be P, no, no, what am I telling? The largest two primes will be P and Q, right?
Not necessary. Because say you take P to be 2, Q to be 3, you get
Yeah.
that PQ is 6,
Okay,
but
five.
P the largest prime is just 5 in PQ factorial.
Makes sense.
Yes. Yes, people, so I'll give you a bit of spoilers. Remembered how we had an congruent to -1 modulo n factorial? Then we had that a to n. Okay, wait, actually. One mod q.
Yeah.
So order of a mod q divided 2n. And then we took n to be a prime p, right? So see, when you do this, what are the possible values that the order can have? We
Two
get
and
that the
One
yes,
P, one P and two and two
not
P.
P. You don't get P
yes,
because P can't. Achha, wait, can P be the order also?
yes. Now like just check out values. When you if you take the order to be 1, you get that a is congruent to -1. Sorry, a is congruent to 1. And then it obviously doesn't make sense that a raised to the power n is congruent to -1. That's like clearly false. Then like similarly you try out this and this and tell me like what is the thing you get? What's the possible value of that?
I guess it has to be either 2 or 2p.
Correct. Because again we see that a raised to the power p was just -1. So yeah, that so we have concluded that the order actually belongs to 2 and 2p. Can you say anything like even beyond this?
Well, if it's 2, it has to be -1.
Yes, that's true. If the order is 2, then a will have to be -1. But anything else? Why can it be 2p? That's the question now. Can it be 2p?
I don't I don't think, because then P would have to divide Q minus 1.
Exactly, exactly. See, so look at the case where the order is actually 2p. So we know that the order of a modulo q divides phi of q, which is equal to q minus 1. But if this clearly cannot be true because p is of greater than q. Does that make sense? Like, why can it not be true?
Yes.
Any question? Yeah.
Wait, which one is Q? One second.
What?
Wait,
All
so
right,
why is
got
P
it,
greater
got it.
than Q?
Oh, see, we
Sorry.
had that n is a prime, right? N is a prime, which is p, and q
Yeah.
is a prime that divides p factorial, right?
Okay. That
P
one.
has to be less than q, less equal q, but in any case, it doesn't make sense, right? So this is a contradiction. So then we finally conclude that order of A modulo Q has to equal to, right? Now try using LTE.
Now LT.
Yes, the star of the movie.
So it has to be true for all primes.
Yes, it has to be true for all primes. What? How can you like conclude from that?
Well, I guess it would be that it's only primes, but I haven't found a proof. But using, but I've tried and checked that lemma I was trying to use until 47. So that means that it can't have any composite number can't have any prime factors under 47 and still satisfy the condition.
Wait, you tried it by hand till 47.
Yes, it's usually quite simple. Sometimes just n or 2, n plus 1, 2n plus 1 as primes.
Very interesting. Right, that's good progress. I think. Then like try it out. It's not that difficult. Wait, also people, before using LTE, remember like what are the condition of LTE and is it satisfied? Do check that.
Yeah, we got in fact those episodes.
Yes, so I'll write that down anyways. As the order is 2, we conclude that A has to be congruent to -1 modulo Q, and hence Q divides A plus 1. So we have that Q divides A plus 1. Q is not equal to 2 because, yeah, like case of 2 is doable by hand. So
Yeah,
2
but
does what?
it's not right because we found that is odd.
Yeah, exactly. It doesn't work. And Q does not divide 1 and Q does not divide A. So all of these are satisfied. Hence, you can use LT.
Wait, we actually need to check all these all the time.
Yes, like usually you have to because otherwise you keep clowning on the problem. Yes. Keep checking.
Okay. So okay, so you can take the VQ of
Yes,
A to
exactly.
the n plus 1, that's equal to VQ of A
Yes,
plus
exactly.
1 plus the VQ of n.
So is everyone here like familiar with what LT is?
By the way, it's a proof simple of this LT.
Could you just like write it down once? I don't remember the actual.
LT. Yes, yes, yes. Uh, yes. So these are the conditions. Wait, I'll write down the conditions as well. Say that you have two numbers A, B, and N. Then VP of A raised to the power N plus B raised to the power N is equal to VP of A plus B plus VP of N. And like these conditions are to be satisfied that the prime P actually divides A plus B. uh the prime P is not equal to 2 and P does not divide A and P does not divide B. These are the three conditions that need to be satisfied and then you can do this. Yes, sorry, I forgot that N odd is also needed.
Wait, why?
Wait, and yeah, for addition, an odd is also needed because you actually, when you look at the proof, it starts by doing the expansion that this is actually divisible by a plus b, blah, blah, blah. So you actually need n to be odd as well.
Achha, for addition only, right? For
Yes,
subtraction is
yeah, when you have the thing where you are taking VP of a to the n minus b to the n can be even as well.
okay. There were a lot of hints that we have to use LT to be honest.
Yes. See, so here you had like a prime and you had this and this. So
Okay.
this was like good bit of it. VP of sorry people.
Yeah, VQ of A to the n plus 1, right? Or
Yeah, n is a prime p, right?
okay, right. Yeah.
Yes.
So VQ of B is 0. It's just 0.
Yes, but see, q can also be equal to p, right?
That's one case that will be one. But if you consider,
Yes. So, take q not equal to p.
yeah,
You can conclude that this is equal to vq of a plus 1. Also, observe that we have the divisibility condition that a to the p plus 1 is divisible by n factorial, right? So we conclude that this vp actually has to be greater equal vq of n factorial. Does that make sense?
yeah.
And like, see, this already looks a little suspicious because like n factorial is a big number. And you're saying that a plus 1 has more. So see what can you do.
Wasn't A less than n factorial?
What?
A was less than n factorial, right?
Yes, a is less than n.
Okay, so isn't it a direct contradiction?
Wait, why is it a direct contradiction?
How can how can VQ of A plus 1 be greater
A
than VQ?
equal to, like, you can just let a equal n factorial minus 1. And that would
Then
be
that's
Except
only
that
one case.
case.
Then
Except
what?
that's
that.
only one.
Wait, go on. Yes. Aryan, go on.
No, no, I was like that. That's only one case, right? That A equals n factorial minus 1. You can just check that case manually. Yes.
Yes, but
Like
we also have to prove that there is no other case, right? Or like magically if something turns out we are doomed.
no, like you had to prove that A equals n factorial minus 1 was the only P factorial minus 1 was the only solution. So P factorial minus 1 works, and anything other than that will give a VQ less than that P factorial. That's what I'm saying. So it's a contradiction. So you can't
Yeah.
get it.
Not necessarily. It's like we can have 24,
What? 24?
we can have something like 25, which has one factor of 3, and 9, which has two factors of 3, even though 9 is less than 25. Sorry, 24.
Yeah, exactly. That's yes. Aryan, did that make sense?
Okay, right.
Wait, so VQ of A plus 1 is greater than equal to VQ of P factorial.
Yes. Yes, that's what we have concluded.
And A is less than N factorial.
P factorial.
P factorial, sorry. Which is N.
Yes. Yes.
Yeah, I know, pretty suspicious, but
Keep
sometimes that's
keeping
most.
exactly. See, so now the trick is just to let q equal p. Because what happens is this expression is exactly equal to 1. And if a is less than, oh sorry, this is not 1. What am I saying? Oh yeah, this is 1. Sorry. Yes. So see, a is less than p factorial. Wait, it's not less than. I'm sorry, I'm very sorry.
And the VQ of P factor also takes out that 1, so we just get greater than or equal to 0, right?
Yes. Wait.
I'm still confused why we can't conclude straight away from VQ of P factorial thing, because that P factorial will just absorb the A plus 1, right?
The counterexample was 9 and 20. So 9 is 3 square and
Yes.
24 is just 3. But like you in that case you're taking A
But we have
equals
24 factorial, right? It would
no
show.
no 24 is 4 factorial.
Okay.
Yeah, but
Oh, right.
you
Sorry.
have
I got. See, people, when you let Q equal P, you get that VQ of VP of A plus 1 is greater equal 1. Right. So from here we can conclude that it actually divides A plus 1, right?
Isn't VP of A plus 1 plus VP of P greater than equal to VP of P factorial? So VP of P, so Q,
Yes.
so you'll get 1 anyway from there. I mean, if I have not made a mistake.
also, yeah, whenever we did this condition, we considered Q is not equal to P, right?
Yes, people. Yes. See this. You have this expression. So the equality is held when can the equality be held? That's the next question we have. Because see, you have when will you have that VQ of A plus 1 is equal to VQ of A plus 1 plus VQ of P equal to VQ of P factorial. Is this possibly achievable? So see, when the prime Q is less than P, what you get that this expression is straight up 0, and then you have then you get this expression is greater equal. Now we consider the case where the prime Q is actually equal to P. Wait, what's this doing? Yeah. Yes. So we get that VP of A plus 1 plus 1 is greater equal VP of P factorial, which is equal to 1.
So VP of A plus 1 is greater than equal to 0,
Yes.
which is true for any
Yes.
number.
Yes. Wait, where did I miss?
I mean, can we use legendaries here or something? Because VQ of P factorial.
Yeah. Wait, let me recall my solution. Yes, sorry. I'm very sorry for this. Yes, see. So is the case of this clear that here we can directly conclude that the VQ that VQ of A plus 1 is greater equal VQ of n P factorial, right? This is true, people.
Yes.
Yes. And so from this, see what we uh so this then we get this thing. So we get this thing. Does that work? Yeah. Yes, exactly. Okay, fine. See, additionally, we have that VP of A plus 1 is greater equal 1. Because we had that P divides A plus 1, right? That's the reason we used LTE. Wait, did that make sense?
I mean, you mean Q here, right?
Yes, I am talking about the case when Q is equal to P.
Okay.
We had this thing. And see, to use LTE, one of the conditions was that Q divides A plus 1.
Yes, that's true.
Right. So VQ of A plus 1 had to be greater equal 1.
Yes.
Yes. And then if we take Q equal to P, this condition still holds. So VP of A plus 1 is greater equal 1.
Yes.
Yes. So we have concluded that VQ of A plus 1 is greater equal VP of P factorial for all primes, right? For all primes Q. Because observe that this expression is just 1 and we had that this is greater equal at P.
Yeah.
So like, wait, did that make sense to everyone or was it not understandable? Did that make sense? Yes, I'll take that as a yes. So we can conclude that P factorial divides A plus 1. Does that make sense? Because we have that VQ of this is always greater equal. Like in general, if you have VP of A is greater equal VP of B for all primes that divide like this thing, for all primes that divide this, so you can conclude that B actually divides A. Like,
Wait, so first of all, you wrote that VQ of A plus 1 is greater than equal to VP of P factorial. Then you magically erased P and wrote Q instead.
oh no, that was not magical. Like, see, do you remember this thing we did here by LT?
Oh, yeah. Okay.
Yeah, so that was not magical. It was like from here. I'm sorry, I'll write it in one place. So for primes less than P by LTE.
Okay, so for all primes less than P, huh?
Yes, so for all primes less than P, we by LTE, we have concluded that VQ of A plus 1 is greater equal VQ of n factorial, right? And then as we had that VP of A plus 1 is greater equal 1 that we had from the other thing because of this condition. Remember?
So we're just saying it holds for P as well.
Yes, what I'm saying is that this expression holds for P as well because see, this is just equal to VP of P factorial, right?
Yeah.
Oh,
Yes,
now I get
so yes. So we conclude that this holds that VP VQ of A plus 1 is greater equal VQ of P factorial for all primes Q less equal P, right? So from this we can conclude that P factorial actually divides A plus 1. And then we can conclude that A is just equal to P factorial minus 1. Did that make sense? Oh, also, if you people are wondering why we could conclude that thing straight away, see that A is actually less than n factorial. So A was less than P factorial and A plus 1 was divisible by P factorial. So that only leaves one possibility that A is P factorial minus 2, right?
Yeah, yeah.
Yes, this is only for the case where n is a prime. We will talk about odd, general odd things later.
Okay, we just took so much effort just for n equals prime.
Yes. So see, we are done with the case when like 2 divides n. We are done with the case where n is a prime. So what are we left with?
Everything else, I guess.
Yes, everything else that is
N
odd
is a
composite.
product of primes. Odd
Yeah,
primes.
n is an odd composite.
Is odd composite anything easier?
Though
It looks like much harder.
it isn't much harder. It isn't much harder.
Okay, that's what you expect for an n from an n4, right? Yes.
Yes. So
This
like
is
no,
an N4.
Yeah, it's 2005 n4. It's bad.
I mean, it looks so small that it feels like it shouldn't be unless you get to
yes.
the work.
Yes, exactly. Like I'm trying ISLs recently and I've just been very sad because it takes a lot of time. Yes. People any ideas on okay, I'm sorry, I asked to. Yes, so I'll start the problem like how
Can
we
we use
approach
like
this.
extremal, like we take P to be the smallest prime dividing n or P to be the largest prime dividing n?
Yeah, that is in general a good idea. Like looking at extremes is a good idea. But if you try it in this problem, you'll quickly notice that it doesn't help.
Also, can you, okay, it's like a very bad, I guess it's a bad idea, but can you induct on the number of primes?
Number of
Primes. Like you did for one prime, n equals to a prime.
wait,
Then
then
now,
your base case would be a thing with 2 primes.
your base case will be a thing with n prime, one prime, which you have already proven.
Yeah,
Now
but
you,
1 prime works. Are you sure that all odd composites work?
no, I'm just telling that I'm not telling for all composers. I'm telling that the induction on the number of primes that divide, like something
Yes,
like that.
yes. So my question is, what will be your base case?
Yeah, prime equals 1 works, so which you showed. Now you take that n primes, so number of primes that divides n is
Yes.
n.
So your claim is that all odd composites work. That's your claim, right?
Uh, Not necessarily, I guess. That, no, I know that not all odd composites work, but do they wait?
Yes. So we can't induct the way you said we will, right?
I think the problem is hard enough. We should just try to find a new construction for A, which we can show for odd composites.
Great idea. Wait, actually, no, that's actually a good idea. See, so the motivation here is essentially that you try out small cases of composite 9 and 15. So, like, believe me, they're not that hard to try out. And what you can quickly see that both of these do not work. Okay.
Wait, so one second. You are telling us to try at 9 factorial divides a to the 9 plus 1.
Yes.
9 factorial?
Okay, see, like, believe me, it's not that hard.
Bro, okay, if 9, even if 9 factorial is not hard, bro, how can you expect us to do 15 factorial?
See, the point is, I did it by hand when I was trying to solve.
Okay, I guess.
Okay, I'm sorry. See, that's very bad motivation, but yeah. So essentially, we see that like odd stuff is hard to work with. So again, we just apply. So we have A. We again,
Also, one more thing. Are you telling that no odd composites work?
yes, I'll like at this point I'll spoil the problem. Like, see, no odd composite works.
Okay, so can't you just do the same thing which I said, like so prove that n equals 2 does not work? Then take now induct that if
But
k
see,
does
then
not work.
see. Again, then see, your the number of primes equaling one work. So how would you like guarantee by induction that something else would not?
Also, factorials must be hard to deal with induction.
What?
Factorials might be hard to deal with using
No,
induction.
no, no. I am telling induction on the number of primes that divided. Like, see, the thing is, you prove that one prime divides n, so n equals prime work. Now, what I am
Yes.
telling is that suppose two primes, n is a product of two primes. So
Yes.
prove that it does not work. Now suppose consider the case that n equals k and k primes divided means n is the product of k primes. That does
Mm.
not work. Now you prove that if then therefore
I
using that if even if n is the product of k plus one primes it can't work. That's what I'm saying.
Mm. Interesting. So can you prove that it doesn't work?
Like it has to be true because you're telling no odd prime work. So I'm thinking if can it get used.
No. See. Don't take my word. In general, don't take anyone's word on this. Because like there have been multiple times when my friends have scammed me. So don't take anyone's word. Just try to prove it.
But proving PQ itself, like we took like so much work just to prove for P. I mean, PQ should
Yes.
be not an easy task at least.
Yeah, that's true.
But we use like ideas from the previous part for P n prime. I guess that should be helpful.
By the way, can we just do it for 9 and generalize?
How will you generalize that?
Just
Because
asking.
9 is 3 squared. So if you have something like 5 squared, I don't see a generalization. Okay, wait, not even 5 squared. 5 times 7. 5 times. right? Because if you do it for 9, you will use some properties of 3, right? Yes, people. So as I've already spoiled the problem, I'll give you how to start.
Should you use LT again? I'm getting a feeling. Not.
Yes, my solution did not have LTE. In fact, my solution dealt with the case of composites at once. So I did not
Oh,
have.
nice.
Yeah, you can probably try that. Wait. Yeah, there do exist solutions by LTE for the second case as well, but we won't be going over that. See, so let n equal a composite number p raised to the power let n factorial equal. So this expression is clearly true where
Yeah.
we have chosen a p that divides n, right?
Yeah.
Yes.
So I claim that if n is composite, infinitely many, like a lot of solutions exist, not infinitely many, more than one solutions exist. So wait, how do I motivate this? Uh,
So will be like generating I mean solutions, or will there be like a general solution for all?
no, in fact, yeah, we will be showing how you can get a solution. Okay, we won't be constructing the solution explicitly. We will show you that that works. Okay, so now assume that a solution works, that a raised to the power n is actually congruent to -1 modulo vp of, like, okay, let vp of n factorial equal k. So p to the
Then you
k.
have to like change the definition of n factorial, I guess, because you've used k twice.
What? Oh, sorry. Uh, a. Yes.
You've used
Wait,
a
a is in the
also.
problem. Sorry. Uh, what have we not used? X. Yes,
Yeah.
this works.
X.
Yes.
Yes. So see, this works. Now our essential, our claim is that multiple of these A exist, right? So if there is a B such that Bn is congruent to -1 mod the same thing, we would have that An is congruent to Bn, right? Does this make
Yeah.
sense? Yes.
Yes.
So, and then we again had a prime that prime P that divided N. So we can further write N to be Pt congruent to B to the Pt. Does this make sense?
Yeah.
Yeah. So like try finding solutions to this. Like will there exist multiple solutions to this mod P to the K where K is one? And like think simpler. If this solution exists, what other solution will exist? Think simpler. It's not that hard for you.
Wait, but the amount of co-prime stuff will be p to the k minus 1 times p minus 1.
Yes.
So start from p in that. So then we can find 2 where if we take the power of p, then it will be the same. Right?
I'm not sorry. Sorry, I did not get what you were saying.
Because p divides 5,
Yes.
that makes sure that there will be some case like this, right?
Why? Why? So you're saying that we will no. So then you will have to pick a suitable T, right? But T here is fixed.
If we just show a to the p is congruent to b to the p, that means that if we put another t on, it's fine.
Yes, great. That's exactly my point. See, so we just need these solutions, right? And
Yes.
that's equivalent to A by B raised to the P congruent to 1 modulo P to the K, right? And like clearly multiple solutions to these exist by something like primitive roots. Like take a take G to be a primitive root mod P and consider everything, then this has multiple solutions.
And even if it's some 2 power, it has to have multiple solutions because otherwise, by pigeonhole, everything would be a solution.
Yes, good. Yeah, that. Oh yeah, that's very good. I did not realize that one. Yes. So, like, does everyone see why this would imply that there are many solutions?
Wait, can you just like run it by again?
Yes. So, uh, we had an congruent to -1 mod p to the k, right? We wanted another solution of that form, and if both were -1, we would have this thing. Then, as p was a prime that divided n, we write n equal pt. This, and if this, and if this, if we have a solution to this thing, we clearly have a solution to this thing. We can just raise both to the powers of t and get
Yeah,
an
yeah,
n.
correct.
And this thing is equivalent to having a solution to this thing, and that's
Yeah.
like
What was the pigeonhole argument?
the pigeonhole argument was you can raise it to any power, and that congruent to one will have multiple solutions. Because if that's not true, you can just say that everything. See, pigeonhole I don't really make sense much. Wait, Bhairav, what was your pigeonhole argument again? I forgot.
If no two go to the same one, then all of them go to different ones. So then it has to go in cycles of some form. So then A to the P to the K to the M will be A, and then we could get some contradiction from that.
Uh, Wait, but what if? Okay, that would happen. Ah, yes. So see, Bhairav essentially said that if they were like if no two solutions existed, we would essentially have a cycle. That is, say if no two solutions exist, then a square goes to some other number, and this happens, it goes on, and then we eventually hit a again, right? Uh, Aryan, does this make sense? Like, we'll eventually hit this again, right?
Yeah,
Okay,
then
like why is it a problem if you would say?
Yeah. So then he says that then we could get like a raised to the power some weird thing congruent to. See, I don't really see. Okay, wait. Sorry. Did you get the like that argument, the primitive root one?
Yeah,
Yeah,
primitive
this,
works.
the primitive root one, I didn't get it actually.
Ah, okay. See, so you do know that there exists primitive roots mod pk, right?
Okay, yes, yeah. P to the power k has a primitive root.
Yes, you do know that, right? Nishant.
Yeah, hello.
Yes, you know this, right? That it has a primitive root.
Yes, it does.
Now
It
you
does.
now you just consider like all the powers, right?
Yes. Oh, and
And
then all to the power p, they'll all be one.
yes,
Okay. Yeah. Okay. That's nice. Okay.
yes. Now the next thing we'll do is that we'll repeat this. Okay, so we got this thing, then we repeat this with all the primes p that divide n.
And we by CRT get infinite many
Yes,
solutions.
and by CRT divided.
Okay, looks.
Okay, sorry, I took a wrong problem. That I should not have taken this.
Yeah, like
Yeah, sorry.
There's no motivation in. I mean, I can't see anything.
Yes, like most of construction NT is just like motivationless. Like actually, like,
you shouldn't say that you solved this problem.
see if you spend enough time on a problem, everything is motivated. Right, but that does not mean you'd like spend infinite time on one problem, right?
You know what? You should have taken that N8 which we solved, which we tried, like which you solved, the group solved one.
Okay, see, that's even less motivation than this. That's like even less motivation. Yeah. So wait, let's just like quickly wrap up with one problem, like an easy problem. Hopefully,
Most
I don't false remember this one. Yes, this is the problem, people.
wouldn't most constructive NT be CRT?
Yes, it's essentially just CRT and Fermat or Euler. Like just spam those two and you'll eventually be done.
Like, did you practice construction NT from Bond or something?
No, I've never explicitly studied construction.
Okay, interesting.
Yes, people, this is the next problem. It's an easy one. Like if you survive to the last problem, you'll probably like kill this one.
Determine whether or not there is a possibility. This is the right, isn't it?
What?
Wait, what A does not divide B to the n minus n for all positive integers? Obviously, it does not, right? What?
Yes, so prove it. Like exactly my point. Just prove it. It's not.
No, no, like, okay, so you need to prove that if n equals k, a divides a n equals k, there will exist a number bigger than k that a will cannot divide. I guess.
What?
Well, then A would divide B to the
No, what I mean is that suppose a divides b minus one. So, like suppose n equals one works.
Mm,
So we need to
yes.
somehow prove that there exists an n greater than one that does not work, that a does not divide.
Yes.
Like if a, okay, 1 second. So if a divides b minus one, a divides b square minus two. So it's b square minus one. So it's b minus one. So a divides minus one. So yeah, if n equals one works, n equals two doesn't.
So is your answer yes or no?
It's no, like obviously.
Yes. Exactly. Like it obviously doesn't.
I mean, there are like so many options to choose from that eventually it won't work for something. It
Like
Yes.
will
like
divide. It will divide eventually.
yeah, that's the thing. Like for example, you take uh no, did I write it wrong? Something yes. It does not even b to the n.
Will it just
It's just no, like it can't be yes. If it's yes, I will not do maths anymore. But
just be
Okay.
something
Wait.
about
What?
taking will it just be something about taking A and phi, and if they're co-prime, then eventually we can sync it up so that it becomes the same, right?
Yeah, exactly. That's essentially the idea. So you want see you have an wait, what? Yes. You have bn congruent to n mod a, right?
yeah.
So see, this is somewhat of a recursive pattern, like n and n. So whenever you have this like recursive sort of a pattern, exploit that. So look at the sequence b, b to the b, b to the b to the b, like this power time, right? And this eventually becomes constant modulo any integer.
Ah, right. That was
Yes.
That's it.
yeah.
What?
It was a exercise in mod. Prove that this becomes constant, and you take mod five
Oh,
to the end.
yeah.
Yes, exactly. So this eventually becomes constant and well, we add as
By the way, like if you didn't know that thing in mod, that mod five to the end is not that much obvious, I guess.
no,
Is it?
you don't actually have to like know mod to do this. So I'll show you why this works. You have like assume that you have b to the b to the b and a bunch of b's here, right? So what you have to do is phi of phi of phi, a bunch of phi a. And like clearly phi is a decreasing function, right? It will eventually hit one. And after like some time you're done.
Okay. What's the source of this problem?
What?
What's the source?
This I think is wait, what is it's 2007 USA TST problem 4.
Yes, it was a university history, right?
See, such scam problems also occur in the tests.
Yeah, there was one more scam problem in the last PDF.
Yeah, like I have made sure to put a lot of stuff. Okay, see, this is wait, I'll see. So if you have not tried this, no problem, try it. But I'll give you one possible solution, which is so otherworldly. I'm pretty sure you won't think. You see, if you're like what?
So it says, wouldn't every triangle's vertices lie on a parabola?
What?
Wouldn't every triangle's vertices lie on some y equals x squared.
They have given a particular.
Sorry.
No. Okay, see, so I'll give you a very unmotivated solution. In fact, I won't even give you a solution, I'll just give you the answer. Take the vertices to be this, negative this, and okay, now is the fun part. Now is the fun part. 2 raised to the power 4n minus 2 plus 1, comma 2 raised to the power 8n minus 4 plus, like essentially this thing squared. Uh, 2 raised to the power 4n minus 1 plus 1. And like if you take triangles with these vertices, they all clearly lie on the parabola. It satisfies the exact condition. Actually, you get the area to be 2 raised to the power n times 2 raised to the power 4n minus 1 whole square.
Wow, that sounds like a solution that you get by doing lots and lots of examples.
Exactly. That's precisely how I found.
Like the motivation is like you can just see it in the face, you know.
Yes, exactly. It's the entire motivation of this problem is yeah.
Like
Also,
all the problems you took, only one had a motivation. That was, I guess, the first problem.
okay, see, I recently I'm doing this like problems which have no motivation.
Why? Why?
See, because problems which have no motivations are harder than the problems which have motivation. Clearly, so yes.
By the way, are you taking the same session for a combi?
Wait, how do you start?